And the next thing I'm going to ask you to do is shout at me if I try and show you either of the backboards before time to see the pictures. It's fine, you can't see it yet. We'll see how I go with only 2 boards until I get there. So again, the polyhedral products are kind of crammed in because other people do things a bit like this, which helps polyhedral products in. But we'll see how we go. Right, so I like thinking about automorphisms, usually outer automorphisms. G should be probably a finitely generated group. And in fact, unless this talk goes significantly quicker than it ever has before, we aren't going to get onto anything more interesting than a finite rank free group. And I generate my free groups by the first n letters of the alphabet and hope I don't run into examples where I need more than about 5 letters of the alphabet. And then I like to think about the automorphism group, which for the sake of making sure all the definitions have been written down, is a set of isomorphisms G to itself under composition. And I have a collection of examples which you may take away and play with. All in F2. You think you know what I'm up to, you can work out what the examples are going to do if and when I get there. Okay. The point is that they all look like suspiciously similar, but they're not. That one. E goes to B. E goes to inverse. Finally, here are 6 examples. Yes.
So BA is not a relation in the group. I mean, these are isomorphisms, right?
Yeah, these are isomorphisms.
BA is not a relation in the group.
There is something to check if you want to be sure I'm not lying to you. But this is a free group. There's no relations.
Oh, I thought this was an arbitrary. It's FN. I'm
These
sorry.
are all in FN.
I'm sorry. I thought it was per G.
For an arbitrary G, these might not all be.
Right. Okay.
This one works for every G.
I didn't realize it was for a free group.
Yeah. Everything is sort of general, but also most of my work is in and around FN, and this is only a half book, so we're probably staying there. So as we've just identified, this one is just conjugating by A, and that is always an automorphism of any group you can conjugate by anything. The rest of them might not be automorphisms if I had some relations to play with. Free groups, you just have to check surjectivity. If you're very bored, here are 6 things you can check surjectivity of. And then that word, I said outer. Oh no, it was coming. All enough. So yes, we have the inner automorphisms, which are the ones that look like the second example. There is an H, so that for all G, 5G. I'm conjugating by the same thing. It might not be uniquely determined by 5, but the same. And then the facts about this are that it's equal to G mod its center. This is the first isomorphism theorem. And also that it's a normal subgroup. And in fact, it's a normal subgroup. Means I can function by it. Now do. That object is what's called the outer isomorphisms. I think I'm just kind of going to ask you to believe me that automorphisms are a thing that some people find interesting. I tell group theorists that they've bought into the propaganda about symmetries being important. So if you think about sort of symmetries are important here in the thinkers of the groups. And then this is either the strategy of I have a bit I understand, let me quotient it away, or if you like inducing these things by homotopy equivalences of islands, ones. Even if you fix two base points, you might differ by an inner automorphism on what you induce. So this gets you out of base point jail and lets you think about maps which don't fix anything. So if we go back to my list of examples, this one becomes the identity in the outer automorphism group, it was inner. And this one is infinite order in the automorphism group, but finite order as an outer automorphism. This one is the same finite order in both groups. That's the thing which always happens. The rest, and then this one and this one represent the same outer automorphism. Some things you could check if you would like. Great, two out of 3 words done. And then the question that I would like to ask is describe or control, quite a vague question. See out. I'm going to go ahead and put that them of over alpha automorphism. E.g. Here's the spoiler alert for what we might be seeing if I get to the end of the talk. Or get into some nice short exact sequence or this kind of thing. So this is the centralizer. I'm going to drop the subscript as well. In the ambient group, I tend to write capitals for outer automorphisms and lowercase for honest automorphisms. They're not entirely consistently. So for the centralizer, I want to think about I can write the commutator however I like. The outer automorphisms, which commute with my favorite automorphism. And the warning, if you are just thinking about this for the first time, is you might think that if you iterate over all of the representatives of this, then you'll see representatives of everything you see downstairs. And that's true surprisingly often, but not all the time. Not necessarily the image of C ought. Somehow you might say I want to try and take the set. And I think I'm pretty sure this is an example of a pair where you can't swap either of them for a representative and still find some honest point. Although again, it's surprisingly hard to convince yourself of. Okay, why do I want to think about centralizers? I have 3 different reasons, and if you ask me afterwards, I'll tell you which mathematicians think each of them is their primary reason. It's just sitting there being irritating in one parameter and hard to understand. This is really easy to define one parameter family of subgroups, and we haven't got control over it yet. Some people like solving conjugacy problems. And if you split your group up into 2 pieces and you've done it there and there, and now you want to know if you can join your pieces together, then you have this kind of indeterminacy up to a centralizer. So getting some kind of algorithmic control over your centralizer might help there. And the way I came across this was I was thinking about 3-bicyclic groups and their automorphisms, and there's a relationship between some of those automorphisms and this outer centralizer of the defining automorphisms. So here are 3 different reasons you might have come across it, but I hope you'll allow me to talk about this for the next few minutes. So I'm just going to crack on and say what the theorem statement is, and then not read my theorem statement. And then after that, I'll talk about some of the pieces that go into my proof, me and Armando's proof, as well as the proofs of some of the other bits. Can't keep 4 boards at the same time, so we'll have to go. Theorems are going to say who they're due afterwards. So we're just actually going to do a little table. So phi is going to be in FN. And then I want to say something about its centralizer. And then I'll try and remember to say who it's by. And I am also at the end of the theorem statement going to owe you a bunch of definitions. I'm going to write down a load of adjectives and some of the conclusions that you can get from those adjectives. And then afterwards, I'll give you the definitions that I owe you for all of the adjectives. If you are an irreducible morphism, whatever one of them is, your centralizer is virtually cyclic. It's in fact it's virtually the subgroup of the generate. This is in some ways the usual suspects. In 27, the laminations paper, if you know the area. If this is a torsion element, then what you get is virtually finite type. This means it has a finite index subgroup with acts, which has a, in fact, finite dimensional classifying space. I think that's the one. Or it acts nicely, which means with co-compacting with finite stabilizers on it. This is due to some of the other usual suspects. Mm-hmm. 93. If you are unipotent and linear, so many adjectives, I'm very sorry. The same conclusion, you're virtually finite type. Different people. Okay. And me and Armando did is we have removed this adjective from the statement. Same conclusion. So it's went on the archive last year. Right. So I owe you this definition. Are we okay with this definition? I owe you, and then I owe you these definitions.
BF again.
BF and this definition. Error. Start with BF, because that's the one where I'm more likely to interact with the room. So type F is a finite AG1. This implies that you're torsion free. Lots of groups don't have this, but they're still quite nice. So VF is finite index subgroup of B with a finite classifying space. So this is kind of the nicest, yes, homotopic finiteness property you can expect from a group that might have torsion. And these centralizers usually do have torsion. There's one. The rest are out of anythings. Irreducible means that you can't easily break your automorphism into pieces. And the definition is slightly annoying. A priori, I can break my free group up into a free product in many different ways. So I'm carrying around an automorphism such that the phi of GI conjugate to GJ. So the first thing you want to do is say there's no splitting where I have some free factor which is just preserved, at least up to conjugacy. And then you think about it a bit harder and you can have this situation where you're permuting free factors. This is also not allowed. This definition includes both bad things. Yeah, I think if you read this paper, you'll find there's a missing case to do with being both irreducible and torsion, but they are also virtually side by side. Not so hard to add it. Yeah, in fact, they're finite. And then
what's H?
What's H? So this is so you might have something like this where A is preserved and B is mapped over it in some fashion. So in this example, you can have A as a preserved, like the subgroup generated by A as a preserved free factor, but there's no like complementary free factor which is preserved, but that's okay. This is kind of one of the ways out of N is more complicated. You see a preserved subsurface in the mapping class group, then whatever's complementary is also preserved, whereas here you can map on top of the preserved things in non-trivial ways.
Okay, so the GIs are non-trivial and H could be
So
trivial or could not be.
you either need at least one GI, and if you have more than one GI, H can be trivial. If you only have one GI, H must be non-trivial. Otherwise, yeah. Right. Add whichever adjective is necessary. A is at least one. A is one. H. 2 out of 4. Linear growth means that if I look at, I'm going to push it in there, I'm going to run myself into problems. I apply my automorphism several times to my favorite element. And then I'm going to take some kind of length on this, and I want this to be conjugacy length. So I'm in a free group, so I have an easy word metric where I just freely reduce. And to get conjugacy length, I also want to freely reduce at the ends of the word. So I take the shortest, any of the shortest representatives of the conjugacy path and take that length. That just means it's constant on outer automorphisms. Be a pain if I was talking about outer automorphisms and define something which changed when I changed my representative. I'm going to normalize it by K, and then I want to look at the limit as K goes off to infinity. Linear growth means this limit is finite on all G, 0. There's a bunch of ways to say this definition. Usually there's multiple mapping class people in the room, and I think there's at least one today. So you should think of linear growth as like a Dane twist. Dane twists are in fact linearly growing. And then in a mapping class group, you're either periodic, some kind of multi-twist, or there's some exponential behavior somewhere. In out FN, you can see polynomial growth in other degrees. So there's this kind of extra complication. But we're not thinking about that today.
Polynomial growth is that supposed to be like pseudo-Nosov or?
No, so pseudo-Nosov is exponential. So in a math and class group, you get this tripod, I guess, like you're either periodic or you're linearly growing. You're doing some kind of Dane multi-twist, or you've got some pseudo-Nosov behavior. In a free group, irreducible is one of the pseudo-Nosov analogs, as long as you made sure to say it was also growing. So for higher degrees of polynomial growth, you'd start adding another number here. And it's always bounded above by an exponential. Just look at the worst behavior in the ordinary length on the generators, and you can't do worse than that. Okay, one more definition. Unipotent means representation into GL and Z is, which means the eigenvalues are all one on those. So in general, if your X, well, you can see stuff which is in the kernel of this and has bad exponential growth, which would not be unipotent, which might be unipotent even though it's hiding in the Torelli group. But when you restrict polynomial things, it turns out that all of the eigenvalues you see are roots of G. And saying that all one is somehow restricting the periodic behavior you can see. What?
In the representations.
So
Homology. Right.
This is not so hard to achieve. If you take homology with Z mod 3 coefficients, everything in the kernel of that action is, everything polynomially growing in the kernel of that action. Right. Now for the how. I've run myself out of time with definitions. It's a good job I prepared the pictures earlier. Right. So how is by thinking about actions on trees. Mark was encouraging us to do equivariant geometric group theory. So I'm going to talk about how automorphisms act on actions on trees. So ignore this one for the time being. I have prepared two Cayley graphs of the free group on two generators. This one is in the usual AB basis. This one is in the basis A and BA. This might be familiar from an automorphism I just put on board. And these are going to have the same underlying graph in the quotient. And if I start labeling, this one says A and B. This one says A and BA. But these are not the same action on the tree. What do I mean by same action on the tree? I mean G equivariantly isometric. And how might I detect that I've failed to have an equivariant isometry? I think the easiest way is to look at translation rules. So in this one, B is translating up the green vertical axis. And on this side, B goes, it takes here up to that vertex there. And if you track back, the inverse was over here. With a bit more. So over here, B is translating by length 1 every time. Over here, B is translating by length 2 every time. This is bad news for being able to do anything equivariant between these actions. Yeah, but trees are very nice, and there's a theorem by Cullen and Morgan which lets you basically go the other way. Once you understand what these translation length functions could look like, if they're the same, then you can write down an isometry as well. And this is for slightly complicated reasons to do with how the action works. This is actually, you have to apply the inverse of the automorphism I previously said to get this marked version. But details. And so I could keep doing this. I could write down a bunch of other bases and a bunch of roses. And occasionally I'd write down something that was equivariantly isometric. If I replaced B with B inverse, that's like Mark was saying, like flipping around this way. I can swap A and B and do a reflection. But in fact, if we start adding more actions on trees into the picture, we can kind of smoothly move between them. So this one over here is 3 valent, so it definitely isn't isometric to anything I've already drawn. And the idea with this action is it's going to have 2 orbits of edges, 2 orbits of vertices, and 3 orbits of edges, hence the color scheme. And what happens here is A moves round like this, and B moves, I do this. That's supposed to be inverse. B moves around like this. And the other element we're interested in is BA is moving. Not quite matched up the colors right, but in that segment there, it's moving around like that. And if you squint very hard, you might convince yourself that is as you can fold both of these trees. So in this one, I think you want to fold A against B inverse side. And this one, I think you want to fold A against BA equivariantly. And you get both of these. Or the other way, you can collapse edges. You pick the right edge and get back to both of these. This one has a quotient graph that looks like this, with 3 orbits of edges. A goes that way, B goes that way. Nope, goes the other way. B goes that way. And these are like basic points of color vote in outer space, which I have drawn on this board. You can see why I didn't want to do this at the time. And I'll just say that if you have an automorphism, it should be an FN really. The way you can always get a new action by, you can apply your automorphism, and then you can take whatever action you first had, and you can always get new ones like this. Irritatingly, the action switches sides. If you were doing left actions on your trees, you're now doing right actions on the space of actions, or vice versa. So you can pick your poison there. Right, so here is the space. This was also the other way. So this point here, I can't draw infinite trees, so I've labeled them by the quotient graphs. So it's supposed to look like a fairy triangulation, but also it needs these green fins sticking up. So it's a bit skewer. So in the middle, we've got this one. It collapses. If you collapse one edge over here, if you collapse the other edge, it collapses to this one. If you're bored, you can work out what the basis must be there if you collapse the other edge. These green bits sticking up are these barbell things. And you can always just collapse them down. If you look at it from the top, it looks more like this. And this red thing I've drawn is a slightly better behaved space. This has missing vertices and edges in its simplicial structure. So I've run myself out of time. That's all right. The pictures are nice. So I will say, maybe out loud, a few words about how this proof goes, and then a few words about how our proof goes. So to understand out FN, you can think about this whole space. To understand centralizers in out FN, you can use the fact that if you have an action on a space and GH equals HG, and you have a fixed point, then the H's play nicely with the fixed points. You have to do it the right way around. GHX is HGX, and if that was fixed, that is HX, which means that HX was another fixed point for the action of G. So you can think about the centralizer acting on the set of fixed points. And the theory is you get a good enough hold of what that subcomplex looks like. And you can extract these kind of properties. And then ours is kind of.
Say that we're supposed to think of the centralizers acting on this outer space, right?
Yep.
I mean, the outer automorphism is acting on this outer space, and then the centralizer is acting on its fixed points, right? So show me one Yeah. Give me. Where's an outer automorphism?
So,
Moves along this dual tree.
so,
Oh, I see, it was like what you were going into there.
yeah, so it moves, in fact, the opposite of the one you think for rotating reasons. So B goes to BA inverse, moves from this action to this action, which is moving from this point here to this point here. This is an infinite order element, so it doesn't have a fixed point in outer space. Finite order elements all have fixed points. Nielsen realization for outer fun is easier than Nielsen realization for cross groups. And then I'll say like half of that thought about the proof in the linear case. The punchline is it's more like JS data than I just said. Linear, nice fixed point on boundary. So this is called the parabolic orbit theorem. There's some kind of very canonical, or almost up to messing around with metric canonical point in the boundary of outer space with Z edge stabilizers. And this is actually preserved by all of the centralizer. And then this is shown and listed in a couple of papers, depending on exactly how you want to say it to look. And then there's a complicated but useful paper by Zhang, which almost gets you like speed of some restriction. This is finite index. This is not a problem. Getting control of this is a bit of a pain, but that's been a pain in Handel. Okay, that's exactly what we needed. And this is, yeah, this is somehow comes from the fact that if you have an action on a tree and you have a subgroup of outer automorphisms preserving it, you can lift that action. You take the pre-image in the automorphism group, and that acts on the tree like really compatibly with the action you first defined.